Thank you for coming. Today, I will introduce a new analytical index for the similarity rating test in Qualia structure. So this new index is called magnitude. So I will suggest a new measurement, and this index is a measure that can quantify structural diversity. Throughout this presentation, I will share insights regarding what magnitude is, how it can be applied to real data, what kind of problems we face when we apply to real data, and how we might solve these problems. Ultimately, the goal of this presentation is to enable the audience to apply this measure to their own datasets. So let me begin with an introduction. So when conducting a typical experiment on Qualia structure, we generally follow steps like these. So first, we conduct a similarity rating test. From the responses obtained, we calculate the similarity matrix. And we then analyze this matrix to understand the structural characteristics and to compare and examine those characteristics. So there has been two primary methods for analysis so far. So one is MDS and the other is GWOT. MDS allows us to visualize the structural characteristics by assigning labels to elements in a special configurations. By observing the relative positions of elements, we can qualitatively grasp whether the structures are similar or not. However, because MDS is inherently qualitative, it can be misleading. Structures that appear different may actually have the same characteristics and vice versa. Thus, interpretation is challenging. And GWOT, on the other hand, enable us to quantitatively evaluate how similar two structures are in an unsupervised manner when they exist in different spaces. Because of this, GWOT is primarily used to compare two structures, and it cannot be applied to a single structure. Also, since it is an optimization method, it may yield different results when the number of trials is too low. In addition, the computational cost is really expensive. So taking these issues into account, we propose a new metric index called magnitude. Magnitude is a measure of structural diversity defined on enriched categories. It has been shown to correspond naturally to diversity indices used in other domains. Of course, it is also applicable to metric spaces. Our motivation is based on the assumption of Qualia structures. We want to measure the richness and diversity of Qualia structure by evaluating the diversity of phenomenological structures. So MDS and GWOT could only define differences between structures or had difficulty quantifying them completely. But magnitude can achieve this. So magnitude is quantitative and can be applied to a single structure. And also it's non-optimization based method. So it's more stable and it can be used in combination with MDS and GWOT. We won't go into detail about the mathematical properties or derivation here. If you are interested in, so I encourage you to read the paper by Tom Leinster here and or join our discussions later. And now let me explain how magnitude is actually calculated. The calculation procedure is as follows. First, we begin by constructing a dissimilarity matrix. Let's assume it is a matrix with values ranging from 0 to 7. And when then convert this matrix into distances using some transformation. And using this formula, we convert it into a matrix ZA. Leinster refers to this as a similarity matrix, but since this name may be confusing, so I call it just a ZA here. And we take the inverse matrix of this ZA and take the sum of the elements of inverse matrix and gives us the magnitude. So, and here is a conceptual image of the calculation. So this is a dissimilarity matrix. And in this case, I multiplied the dissimilarity matrix values by 1 to obtain the distances. So the image is the same. And this gives us the ZA. And then the impulse matrix looks like this. So summing these elements yields a magnitude 3.4. So this is how calculate the magnitude. So I will show the results of applying magnitude to real data now. So yes, we conducted an online similarity task with 120 participants, and time course is like that. The stimuli consisted of 10 color-related words and 13 emotion-related words, totaling 23 words. Participants were presented with pairs of these words and asked to rate their similarity. And the subject answered all combinations. We also collected scores from a psychological scale for depression called BDI. Based on their scores, the top 60 participants were categorized into a high depressive group and the bottom 60 into a low depressive group. Okay, so then I will show the result. The first we show the average dissimilarity matrices for each group. So this shows the dissimilarity. So lighter colors indicates the participant judged the items as more similar. The overall patterns looks like a little bit similar between these two groups. However, when we focus only on the combinations of color-related words pairs, the high depressive group tend to show darker colors, suggesting that they judged the color words as less similar than low depressive group. In other words, while the overall patterns looks like similar, but we get the impression that there are differences in degree of certain pairs. Then let's look at the correlation between depression levels and participants' responses. Please ignore the numbers. And the color in this plot represents the correlation coefficients between dissimilarity and depression level. Red and blue indicates the opposite tendencies. An interesting pattern emerges for combinations of color-related words versus other color and emotions, and emotions. The correlations with depression levels are in opposite directions. So this suggests or indicates there are some structural differences. So when we have this kind of impression, let's see the MDS results. So the high depression groups seem to show a closer proximity between these green emotional words and red colors words, but it is kind of hard to interpret clearly. And after that, using GWOT and increasing the number of trials, we achieved 100% alignment. The results suggest that the two structures, high depressions and low depressions, are completely matched. So to summarize these results, observations from the dissimilarity matrix and correlations with depression levels were not reflected in the results from MDS and GWT. Of course, more detailed observations of these results are possible, but if we naively accept only the optimized result from GWT, we would conclude that there is no difference between the two structures. So after that, let's see the magnitude. So, so this is the actual values of magnitude. After averaging the dissimilarity matrices, we calculated the magnitude. Before interpreting the results, let me explain the concept of magnitude a little bit. So magnitude reflects the number of categories. When participants' responses are interpreted such that similar items belong to the same category and different items to separate ones. So a higher magnitude means that participants more finely distinguish the stimuli, which implies greater diversity. Let's see the result. So this column shows the magnitude calculated for all word combinations. Since there are 23 stimuli, the ideal value, if participants perfectly distinguished all words, would be 23. However, the actual values were 12.81 and 12.4, meaning that participants distinguished only a little more than half of the stimuli as categories. And now let's look the combinations on the color and color-related words, which were distinctive in the dissymmetry matrix. Ideally, the maximum magnitude here would be 10 because stimuli is only 10. In reality, the values were 5.98 and 6.94. So the difference between groups is about 1. This suggests that the high depressive group had one more clusters of color perception, meaning they had greater color diversity than lower depressive group. The high depressive group perceives color more finely. So this is the result of meaning among subjects. To check whether this property is consistent across individuals, let's look at this scatter plot. On the x-axis, we have a group, low or high, and on the y-axis is the magnitude. Each dot represents on one participant. And the red point is, I will show you that later, but for some reason, we can't calculate the inverse matrix well. Okay, we calculated the magnitude for each participant and plotted the distribution here. Okay, so please look at the leftmost plot. When all words combinations are used, the distribution does not change so much between groups. The center plot shows emotion-related word combinations. Again, not so much. The rightmost plot for color-related word combinations shows a relatively noticeable shift in the median, although it might not reach statistical significance. However, we can see that individual differences are quite large all among the word types. And finally, let's compare this with the result from dissimilarity matrices. So this one, as shown here, we can capture qualitative differences that traditional analysis could not express. The difference of color appears between high depressive and low depressive. So in this way, magnitude can capture structural information that MDS and GWT can't capture. And thus, it can be used complementary with MDS and GWT. So yeah, brief summary is, yeah, and this is a small amount of calculation because it's not an optimizing process. And it's also applicable to other similarity tasks. But there is also limitations. As mentioned earlier, we still need to discuss how much of a difference should be considered significant. We don't know, we can say just one difference can be said as a difference. Also, participants' responses do not necessarily satisfy the axiom of distance, so which may cause problems. Furthermore, the process of computing the inverse matrix is low in interpretability. So now let's look at the issues that arise when we apply magnitude to real data and how we might address them. Okay, so also I plan to discuss this in more detail on another occasion. In general, I feel dissimilarity matrices averaged at the group level among subjects do not cause significant problems when calculating magnitude. However, when we try to calculate magnitude for individual participants, we get quite different results, and some cases are difficult to compute or interpret. Specifically, for more individuals, the inverse matrices can't be computed, or the resulting magnitude diverges to positive or negative infinity. Now, do you want to say something?
No?
Okay, because I see your hand off, your mute, so.
No problem.
Okay. Okay. Yes, so here is a typical example of a participant whose magnitude could be computed without problems. On the left is a dissimilarity matrix and distance matrix. In the center is ZA, and on the right is inverse matrix. The magnitude for this participant was 12.2. And let's look at the case where the inverse matrix cannot be computed. The determinant of the matrix becomes 0, making it undefined by definition. As countermeasure 1, we removed duplicated rows and columns from the responses and recompute. This enables computation for more than half or something the participants. But even after this procedure, some matrices still cannot be inverted. This presumably due to the existence of laws in a linear relationship, even if they are not duplicates. Currently, we use a pseudo-inverse in such cases, but the interpretation of these results remain under discussion. So let me show you examples. So these participants gave identical responses for red and yellow and other pairs here in the dissimilarity matrix. And we kept only red and deleted other duplicated rows to perform their computation. And we can compute the inverse matrix. And magnitude was around 4. Yes, and in the next case, even after deleting duplicates, some rows remained linearly dependent. So we have to use the pseudo-inverse. So we can see there is a duplication between red, orange, yellow, or brown, or black, or something. And after cutting these rows out, there remain some linear relationships. Chan, do you have?
Yeah, if it's clarification.
Yeah, clarification question. So just to make sure I understand this matrix, this participant rated all the colors as uniformly similar to each other. Is this what's going on here?
Can you say it again?
So this subject 11, they rated all the colors as similar to each other.
Yes, that's right. And the combination of color and emotions are completely different, mainly.
Oh, okay. And then only emotion had some kind of changed. I see.
Complicated or something. Yeah.
Thank you.
Yeah. In 120 subjects, there is some people answers like that. So some people's answers using only 0 or 7. Sometimes happens.
Then it will be easy.
Okay. Yes, so this is another case. We can't calculate inverse matrix. And Yes, another issue is that of negative or infinite magnitudes. How we should interpret these cases are still under discussions. However, this result arise from the formal definition, so they are not necessary calculation errors. Even if two structures are completely isomorphic, in other words, identical in configuration but differing only in scale, magnitude can still produce different value. For example, computing distances directly from the dissimilarity matrix versus computing after scaling the matrix by a factor of 10 can yield different, even divergent or negative values. Therefore, selecting an appropriate method for computing distances is really important. This plot shows for each participant the ratio used to scale the dissimilarity matrix on the x-axis and the resulting magnitude on the y-axis. And red dots indicates participants whose inverse matrices could not be computed. We can see the different ratios yield different magnitudes for all participants, and for some participants, like 2 and 7 and 32 or something, the values diverge at specific ratios. And yes, here is an example of a participant with negative magnitude. Even though the dissimilarity matrix does not contain extreme values, like only answers using only 0 or 7, the magnitude becomes negative. Yeah, and we are currently considering alternative measures such as spread instead of magnitude. Spread is like magnitude. Spread is a diversity index defined on structures. Both magnitude and spread are approximations of the maximal diversity on a structure. Spread was proposed later than magnitude as a more robust index. It doesn't require matrix inversion, and its range is from 0 to the total number of similar n, so negative or divergent values do not occur. In the future, we also plan to compute spread. At the same time, we were also considering the possibility that the point at which magnitude becomes negative or divergent might reflect some psychological characteristics. So yes, I will investigate this possibility as well. Yes, this is the end of presentation, so thank you.